Hello, I just wanted to make a video going through all of the reactions in the alkene chapter. So yeah, let's get into it. The first one is hydrohalogenation that I have written here. Our reagents for this are going to be HX. So X is just going to be a halogen. So usually you're going to see HBr or HCl. You could see HF, but this isn't super reactive, so we're just going to leave that one out because you'll probably just see these ones. And this reaction is Markovnikov, and it does have carbocation rearrangement. So our first step in this is that our double bond is going to come and pick up this hydrogen. Let me draw that a little better. Right here. And then the electrons from this bond connecting the hydrogen and bromine are going to go back to the bromine. Now at this point, we're wondering, are we going to add the hydrogen to this carbon, or are we going to add it to this carbon? So because this is Markovnikov, that means that my hydrogen is going to be added to the less substituted side. And whatever else I'm adding, so in this case a bromine, is going to go to the more substituted side. So I look at my two carbons. This one has 2 carbons coming from it. This one only has 1. So my hydrogen will go to the less substituted side, which is this one. So I will go ahead and put that right here. And then over here, because right here I had 1, 2, 3, there already was a hydrogen here, 4 bonds, and now this double bond is getting taken to make this bond with the hydrogen. Those electrons are moving over. Now this carbon only has 1, 2, and that same existing hydrogen. It only has 3 bonds, so that's why a carbocation goes there. Now at this point, you want to check for rearrangement. Anytime that you have a carbocation, you want to pause and see, can it rearrange? So in this case, it can. There is a hydrogen right here, and it can move down into this spot. I'm just going to delete that hydrogen for now. It's going to move down into this spot so that this has 4 hydrogens again, and then over here we'll only have 3. So that will give me this. And then this bromine right here that took the electrons, we're going to use that Br minus to attack this positive charge. And this bromine can attack either from the front or from the back. So I could get either this, or I could get this. I'll get a racemic mixture of these products. Okay, so let's do that one with one more molecule really quick. So let's do it with this ring. So we're going to do HBr. So at this point, it doesn't matter which side our hydrogen gets added to because both sides are equal. They have the same number of substituents. So this Markovnikov doesn't really apply here. So let's just put R positive on this one, and then my Br minus will come and attack here, and I will get this. If I wanted to, I could draw the stereochemistry like I did in this first problem with the wedges and dashes, or just depending on the question type, I could just draw it as a line like I did here. Okay, so let's move on to hydration. My reagents for this one are going to be H2SO4 with H2O, or sometimes you might just see it written as H3O+. This one is Markovnikov, and it also can rearrange with a carbocation. Me personally, whenever I see this as my reagent, I like to just cross it out and think of it as H3O+. Because when you put sulfuric acid in water, it's just going to create H3O+, and I just think it makes the mechanism a little bit easier to follow when you do it this way. So for this one, I'm going to take my double bond, grab a hydrogen, and then these electrons from this bond are going to go back to the oxygen. And then because it follows Markovnikov, my H is going to go to the less substituted side, and then that will create a carbocation on the more substituted side. So I will get this, similar to the last one, and then same thing, we'll just have a hydride shift so that I get this. And then here in this first step, we created water, and so that water is just going to come and attack right here. Same thing as the last one, this could attack from either the top or the bottom. So it could create the wedge or it could be on the dash. For simplicity, I'm just going to draw it on a line, but hopefully you get the gist. Okay, so then I have this, and I'm just going to take another water molecule and extract one of these protons. And I get my final answer. Sometimes in the textbook, you'll see that they omit this step. They'll just kind of go from this OH to, or this water to this OH. But yeah, this is all that's happening. Just another water molecule will come and extract that proton. Okay, let's do hydration with a ring. So I'm just going to draw in H3O+. My ring is going to grab a my alkene is going to grab a hydrogen. Then the electrons from this bond are going to go to the oxygen. In this case, it doesn't matter which side that the hydrogen goes to and which side my carbocation is on, because it is symmetrical. Okay, now my water is going to attach here. I'm really bad at drawing lone pairs on oxygen, so if you catch that, I'm sorry, they are there, I promise. Okay, so then I'm just going to have another water come, grab a hydrogen. These kick back to my oxygen, making it happy. If you're ever wondering why why positive signs are just showing up or disappearing, it all goes back to formal charge. So just calculate formal charge and that will show you why there is a positive or why the positive disappeared. So then I just get OH. And remember, this OH could attack from either the front or the back, so I can get both this product or this product. Perfect. Let's move on to halogenation. So my reagents for this one is going to be X2. And remember, X is a halogen. So we're going to look for Br2 or Cl2. And for this one, Markovnikov does not apply. There's no carbocation, and rearrangement is not possible. But what we do want to remember about this one is that it has an anti-configuration. And all that means is that whatever things I'm adding, so whatever two things I'm adding, will be on different planes. Okay, so my first step for this one is that this double bond is going to grab a bromine. And this one's a little bit weird, but this bromine is actually going to grab this double bond back. And then these electrons in this bond are going to go to my other bromine. And that's going to create something that looks like this. So at this point, this Br minus is going to come and attack this ring. I have a dipole here going from here or here, and so it's just going to attack one of these carbons. And when I do this, let's see, eraser, okay. When I do this, the bond right here to whatever carbon that it's attaching to is going to go back to the bromine. If you have a hard time visualizing this, something that you can do is just erase this bond. Oh, or erase the whole thing. Let's just erase this bond. It makes it a little bit easier to visualize with this bromine attaching to this one and this bromine being attached to this outside one. And I get this. So back to what I was saying earlier about this being anti, it means that whatever things I added are going to be on different planes. So my two products will be this and this. Okay, now let's do this with a ring really quick. So my double bond is going to grab back. This bond is going to go to the bromine. And then my Br minus is just going to attack one of these. And then this bond right here is going to go back to the bromine. And if I need to, I can erase this bond just so I remember where things are going. And then my products for this one will be Br, and that. Perfect. Okay, now let's do halohydrin formation. This one is going to be very similar to the last one. There is a difference in reagents. It's going to be Br2, well, actually, let's make this more generalized. It's going to be X2 with H2O, X being the halogen, so Br2 or Cl2. Same thing for this one. It's going to be anti, no Markovnikov, no carbocation rearrangements, none of that. So my first step for this one is going to be exactly like the last. These are going to grab each other. And this step is where it gets different than the last reaction. So instead of that Br minus attacking, this OH, okay, I keep calling it OH, this water is going to be what's attacking. So it's going to come over and attack here to our more substituted side. That's important. let's make a note of that. Water attacks more substituted side. Because this carbon has 1, 2, 3 things coming off of it, whereas this one only has 1, 2. Okay, and then the carbons that are connecting, the electrons coming from this carbon to our bromine are going to kick back to this bromine. Let's erase this bond. Just the bond. Okay. And then I get that. So then I'm going to take a water molecule and just grab a proton so that I get my BrOH. And then the two things that I added on this one were this OH and this Br, and it's anti, so I will get this and this as my products. Something about anti is that anytime you have a ring that gets opened, so like in this one right here when we had this ring and it gets opened, anytime you have that, it's going to have an anti configuration just because of how the ring splits open. Okay, let's do that for this one. So for this one, because we have a symmetrical molecule, it doesn't necessarily matter which one the OH goes on and which one the bromine goes on. Our water can attack either side because they're equal. Let's have it attack this top one. This bond goes to the bromine. And my drawing is getting ugly, but you get the gist. We will get OH, Br plus that. Perfect. Okay, let's go to oxymercuration and reduction. So my reagents for this one are going to be HgOAc2 and NaBH4. So for this one, you don't need to know the mechanism. What you want to remember is that it is Markovnikov. There is no rearrangement possible. There's no carbocation, and it is anti. So this one's kind of unique because we don't have to remember the mechanism. There's just a couple things we need to remember about this reaction. First thing, definitely need to memorize the reagents and the name of the reaction. And then it's Markovnikov, so I'm going to be adding an H to the less substituted side. And then I need to memorize that I'm going to be adding an OH to the more substituted side. So I look at my alkene and I have these two options. This one on the right is my less substituted side. This one on the left is my more substituted side. So all I'm going to do is wherever my alkene was, put an OH on my more substituted side, and then I'm adding a hydrogen on my less substituted side. And then because it's anti, I know that these two things that I added are going to be on different planes. So I will get this plus this. Okay, so for this one, because they're even, it doesn't really matter. which one? Oh, hello, H, okay. We could get that. I could put the OH on the bottom one or on the top one, but because this molecule is symmetrical, you'd realize that if you just rotate the molecule, it would be the exact same molecule. Okay, let's do hydroboration and oxidation. So for this one, what we need to remember is that this one is anti-Markovnikov. And for this one, we're going to be adding an H on our more substituted carbon. And then for this one specifically, I need to memorize that I'm adding an OH to my less substituted side. And then I also need to remember that this is syn addition. So whatever two things I add, in this case, my hydrogen and my OH, are going to be on the same plane. So they're both going to be wedges or they're both going to be dashes. And then the reagents for this one are going to be BH3, NaOH, H2O2. So I look, this is my less substituted side, and this one over here is my more substituted side. So I will just go ahead and add my OH over here, my H over here. And then it is syn, so I know I'm going to get this and this. Let's do this to the ring. Oh, okay, I keep doing that. There we go. Easy peasy, hopefully so. Alrighty. Let's do catalytic hydrogenation. So for this one, Markovnikov does not apply. There's no carbocation, no rearrangement possible. We do want to remember that this is syn addition and that we are adding 2 hydrogens. My reagents for this one are going to be H2 and PT, PD, Ni. Could be one of these 3 metals. And so all I'm going to do is on this carbon and this carbon, I'm just going to add a hydrogen, and that will just take away my double bond. Because it's syn addition, I know that the hydrogens that I added, sorry, that was kind of an ugly wedge. Okay, there we go. They will be on the same plane. This might seem a little bit redundant, but it is worth memorizing because they will find ways to ask you about this and make sure that you know that it's syn addition. Yeah, okay, so for the ring, let's do platinum, and I could get this, or I could get this. But But if I were to ignore my hydrogens, we can see that this reaction basically just removes the double bond. For Wilkinson's catalyst, it's literally the exact same thing. I will draw the differences. Wilkinson's, oh, did I spell that right? Yes, I did. Wilkinson's catalyst. The only difference is going to be our reagent is H2 and Wilkinson's. That's it. Everything else, exactly the same. Dr. Hom's videos do a great job of explaining the how the catalytic hydrogenation works and how you have a molecule kind of going down onto a metal sheet. So if you need further explanation on that, I recommend watching his videos, or feel free to reach out to me and I can try and explain it too. But yeah, this one's pretty easy. Okay, let's do epoxidation. On your chart that is on page 25 of the lecture notes, it has epoxidation and anti-dihydroxylation grouped together. For this one, I'm going to treat them as separate reactions, but you can put them together. So for this one, our reagents are going to be peroxy acids. And the most common one that you're going to see is MCPBA. But what you want to watch out for is anything that has the formula RCO3H. Remember that this R can be any carbon group. So it could be like CH3, it could be an ethyl group, things like that. Sometimes it will even just say peroxy acid. And yeah, you'll just treat it the same way. For this one, there's no Markovnikov, no carbocation rearrangement. Yeah, none of that. So all I'm going to do for this one, super simple. I'm just going to add an epoxide ring where my double bond was. I could even put it this way if I really wanted. That looks a little better. And these are going to be on the same side. Oops. Okay. So I'd get this and this. Do that for the ring. Easy enough, hopefully. Okay, and then for the dihydroxylation, we could either have H3O plus, or we could have OH minus. And this one is anti. So for this one, you actually have to start with an epoxide ring. So that's why these two usually get grouped together, but you can have them as separate reactions. But because you have to start with an epoxide ring, you could make epoxidation your first step, with dihydroxylation being your second step. So let's do this with acid first. Actually, let me draw it out. H3O plus. And my electrons from my oxygen are just going to come grab a hydrogen. These electrons from this bond are going to kick back to my oxygen. And I get this. And then right in this first step, I created water. Okay, and then this water is just going to go over here and attack. Same thing with my other ones. If I have a hard time visualizing this, I can just erase this right here. And then we'll just have another water molecule come pick up one of these protons. These electrons from this bond go back to my oxygen. And the clue to this was that we had a ring and we opened it, and so it's going to be anti. So I will get both this product and this product. And then if I were to do this for my ring, get that. Perfect. Okay, now let's do syn dihydroxylation. My reagents for this one could be either OSO4 or KMNO4 with NaHSO3, H2O in my second step. And for this one, we just need to remember that it is syn addition. There's no carbocations, no Markovnikov, no rearrangement for this one. For this one, I just want to remember that I am adding 2 OHs, 1 to each of my carbons that's on my double bond, and that they're going to be syn. So I just look at this carbon, and all I'm going to do is add OHs to those ones. And then I will also get this. And then for my ring, we will get that. Hopefully not too bad. Okay, last one, ozonolysis. So in my first step, I will have O3, and in my second step, I will have either SEM2 or zinc with H3O+. For this one, there's no Markovnikov, no carbocation, no rearrangement, no anti or syn, nothing. For this one, I am going to take some imaginary scissors, and I'm just going to cut my double bond right in half. And let's actually do this with the eraser. Just going to cut it in half. And then wherever I cut it in half, that like the side that the double bond is on, I'm just going to add an oxygen. Looks kind of weird. I know, I'm sorry. But if you can visualize it, this is kind of where this is going. So if I redraw this better, I've created 2 different molecules. I've created this one, and then I've also created this one. So let's draw it a little bit nicer. Actually, this one, let's put it here, make it look even nicer. And then right here, I do have a hydrogen. That hydrogen was already here when this reaction started, but because I now have this carbonyl group, I'm just going to make it into this nice, beautiful aldehyde. And then over here, I have this, but I'm going to add just my 2 hydrogens that, again, they were already here at the beginning of the reaction, but now I'm just going to draw them in. And this actually is called formaldehyde, which happens when you have a double bond that is on the end. Now let's do that with the ring, which is a little bit trickier, but that's okay. So again, I'm just going to take my imaginary scissors, cut here. Let's do it with the eraser, cut here. And I'm going to add an oxygen between where I cut. So now to redraw this one, what I like to do is I just like to count my carbons and number them. So 1, 2, 3, 4, 5, 6, and I cut my ring. So this ring is no longer connected. And so I am going to 1, 2, 3, 4, 5, 6, make it linear. And if I number these 1, 2, 3, 4, 5, 6, now I can see on my number 1 carbon, I have this double bond, and then I will draw in my hydrogen. And then on my number 6 carbon, I also have this. So that would be my answer for that one. Believe that is all of the reactions. Hopefully this was helpful. If you catch any mistakes that I made, feel free to reach out to me, let me know, or if you have any follow-up questions, please message me. Thanks for watching.